Now that we know that atoms need to bond for stability, and that nonmetals need to share electrons to bond with each other, we need to figure out how these atoms actually arrange themselves to create these molecules. So this is how to build a Lewis dot structure. Now, Lewis dot structures are just a model, just like the Bohr model was just a model. It's always going to be a little more complicated than what we're doing. However, for the particular molecules that we're looking at, the rules of building a Lewis dot structure can be taken absolutely. So first step, and we'll use CHCl3 as an example as we go along. The first step is to choose the least electronegative atom. The least electronegative atom. Except for hydrogen, though. We've got to remember that hydrogen can only handle 2 electrons. And since one bond consists of 2 electrons, hydrogen can only have 1 bond. So we're going to take the least electronegative atom except for hydrogen and put that right in the center. Everything else will arrange itself around that. Sometimes you'll have larger molecules that have a lot of carbons, in which case you would use a carbon chain as your central atoms and go from there. So my next step is to arrange all of the other atoms roughly equally distant from each other around the central atom. And I'm going to attach them all with single bonds. Right, so got 3 chlorines and 1 hydrogen. Okay, now my next step is to make sure that each atom has its own octet. So I can see that carbon is fine. Carbon having 4 bonds around it sees 8 electrons as its own. So I need to put lone pairs in all of the places that don't have bonds that need it. So all of these chlorines are going to get 3 lone pairs. So they can have an octet. And hydrogen doesn't need any lone pairs because it follows the duet rule. It is perfectly happy with the 2 electrons in that 1 bond. Okay, that's a great preliminary step. However, all we focused on was how many electrons we needed to complete the structure. We didn't take into account the fact that each atom only contributes so many electrons. So the next step is to calculate the electrons available. To see if your structure is valid. Oh. Excuse me, this should not be available. This should be forming a full octet. So we're adding lone pairs until each atom has a full octet. And then we calculate how many electrons are available. Right. So we have, from the chlorines here, we have 3 chlorines, and each of them, from their position on the periodic table, contributes 7 electrons. So that's 21 electrons. Hydrogen contributes 1 electron, and then carbon contributes 4 electrons. And so that gives us 26 electrons to work with. Let's go ahead and count them up. Each bond is 2 electrons, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. And so we're fine. This is a completely valid structure because we're not showing any electrons that aren't actually there. So if you have the same number of electrons available as you have in your structure, that's great. Your structure is done. However, sometimes there are fewer electrons. and then you have to start adding double bonds. So let's look at CH2O. So take my least electronegative atom, except for hydrogen, being carbon. I'm going to arrange 3 bonds, one for each atom, and then have space for 1 lone pair on the carbon. That way it has an octet. The hydrogens are fine with their 1 bond, and then the oxygen needs 3 lone pairs to have a complete octet. So let's add up our available electrons, though. So carbon gives us 4 electrons. Oxygen gives us 6 electrons. There's 2 hydrogens, each giving 1, so that's 2 electrons. So we only have 12 electrons to work with. Let's count them up. 2, 4, 6, 8, 10, 12, 14. That's a problem. So now I'm going to have to rearrange this molecule to have a double bond. Now the only choice for that double bond is between carbon and oxygen. Okay, so taking these individually owned electrons, these lone pairs, taking them out and replacing them with a shared pair of electrons between the two will reduce our number of electrons in the drawing. So let's see what that would look like. So carbon has 4 bonds. It sees 8 electrons. It's happy. I've got to put 2 lone pairs on the oxygen to make sure it has an octet. So now let's count up our electrons. 2, 4, 6, 8, 10, 12. Perfect. Now we're done. Let's look at another one. SeO3. So Se is below oxygen on the periodic table, so it's going to go in the middle. And then we've got 3 oxygens. And leave space for a lone pair on the Se, the selenium. Complete the octets of the oxygens. There we go, and let's count up our electrons. So oxygen and selenium are in the same column, so they both contribute 6 electrons each. So we really have just 6 electrons times 4. That gives us 24 electrons. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. We've got to put a double bond. All right, there we go. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Now we have a legitimate structure. But the question we have to ask now is, what's so special about this oxygen? Why did I give the double bond to this oxygen and not either of those? The question is no good reason. I just arbitrarily picked an oxygen. These are all equivalent. So this is a phenomenon called resonance. So you have multiple structure options called resonance structures. Okay, so in this situation, you would, on your lab report, draw all 3 structures, each with the double bond in a different place. Okay, let's look at one more example of that, and that's NO3 here. And it's hard to see, but you'll see on your note sheet that this is an ion. This is a negatively charged ion. So that negative charge gives us 1 extra electron to work with when we're calculating our electrons available. So let's put N in the middle. And arrange our O's around that. calculate our electrons available. So 6 electrons times 3 oxygens gives us 18 electrons, plus 5 from the nitrogen gives us 23 electrons. 23 electrons total. And then we've got 1 electron from the negative charge. So we have, forgive the poor format here, 24 electrons to work with. Well, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. So we must add a double bond, and all of these oxygens are equivalent. So I'm going to draw my 3 resonance structures. Oh, you also want to put this in brackets. If it's an ion, you put it in brackets and write the charge outside the brackets. And if you're drawing multiple resonance structures, you also draw brackets, regardless of whether or not it's an ion. Oh, I'm sorry, this lone pair is no longer there. If we draw the double bond here, see now nitrogen has an octet. If I had kept that lone pair there, that would violate the octet rule. It would be too many electrons. And one more. Oh, I barely gave myself room. There we are.